So we left off on Tuesday introducing the idea of clades, which are a group that includes the ancestor and all of the descendants of that ancestor, right? And this is why I told you maybe, I don't know, half a dozen times that phylogenetically we are fish, because the only way to make fish a clade is if all of the descendants of fish are also fish. And so since the idea is that tetrapods, including humans, evolved from fish, then that would make us fish in order to preserve that as a clade. It would also make birds dinosaurs, so birds are both dinosaurs and fish, and it makes things, I don't know, a little bit interesting in terms of groupings. All right, and then I told you a monophyletic group is synonymous with a clade. And if a clade is a group that includes the ancestor and all of its descendants, what is a monophyletic group? Yeah.
It's a group that includes an ancestor.
And all of the descendants. I love it. So let's just name these organisms 1, 2, 3, and 4, right? So that we know at the end of this branch this is representing an actual organism. Although I don't want to put a name there because I'll run out of space and have to bend the names again. Yeah, Trinity.
Should we draw that?
It doesn't matter. Yeah, it doesn't matter. Thank you. All right. So here is a monophyletic group. And we can tell that that is a monophyletic group because the group contains this ancestor and all of the descendants of that ancestor, right? So this one right here, this is monophyletic. You could also call this what? A clade, right? Beautiful. Nicely done, Kyle. All right. So then I want to show you a paraphyletic group. Okay, this right here is a paraphyletic group.
Wait, wouldn't all its ancestors include that bottom one too?
Well, so no, it's an ancestor and all of the descendants. It doesn't have to include all of the ancestors.
Oh,
It's an ancestor and all of its descendants.
Great grandma and then the rest of it.
Yes,
Gotcha.
everyone
Not
descending
like my
from that
great-great-great,
grandmother.
right?
Correct.
Gotcha.
Yes,
Okay.
absolutely. So this group right here is paraphyletic, and somebody described to me how this group is different. Yeah, Trinity.
It doesn't include all of them?
Yeah. So what we would say here is some descendants. Sorry, not ancestors. Did you mean descendants? Yeah. Okay. So some descendants, and I think it's ENTS. I wrote it as ANTS. I don't know. Some AN. Is everything else right?
Yeah.
Okay. Some descendants left out of the group. Some descendants are left out. Hang on just a moment, Isa. So, if you do not include tetrapods in fish, fish now becomes paraphyletic. Because some of the descendants of that fish are not included in that group. Does that make sense? So in order to keep fish as a monophyletic group, you have to include tetrapods. Alright, Isa.
Isn't it kind of hard to have monophyletics, like finding all the descendants?
It's not necessarily difficult, it becomes strange. It makes it to where your groupings are a little bit strange. Like, when you use the word fish, it has to represent fish and all tetrapods as well. So it becomes strange. I don't know if it's necessarily difficult because it's all based on what we think we know from these phylogenetic trees.
I just comprehended that it's not like every single individual is
No.
I thought you meant like every single fish in this.
No, yeah, just every species. Yeah, Mark.
What is a tetrapod again?
A tetrapod is something with 4 limbs or came from an ancestor that had 4 limbs. So it's amphibians, reptiles, birds, mammals are tetrapods. And then there are some extinct forms that don't fit nicely into one of those 4 categories, but they're still tetrapods.
Probably just thinking now, but basically, like, if all those are specified in your fic, then what's everything else? Because, like,
Well, then everything before, because fish are something novel and different, but it would make every vertebrate a fish. So every vertebrate would also be a fish. Anyways, all right. So this is a paraphyletic grouping, but what about polyphyletic? What does poly, that root mean? Many. It can be two. It just has to be more than one. And so, and then phyletic means ancestry. So now it's a group where you're not including the ancestors. So it would look something like this. Let me change colors. I want to change colors. So, will this one work? Oh, yeah.
Oh my goodness. It doesn't let your child eat. That's fine.
What does that have anything to do with what we're doing?
Come on.
Polyphyletic. So here is a polyphyletic grouping. It is a group, it's containing organisms that are coming from separate ancestries, right? So it's including 1, 2, and 3, and these are coming from basically separate ancestries. So 3 shares a more recent common ancestor with 4 than it does with either 1 and 2. And if you're going to exclude some of these ancestors, you end up getting what's called a polyphyletic grouping. This happens fairly commonly. Isa, you pointed out, isn't it difficult to try to get everything to be monophyletic? It does when you have some complicated phylogenies. A lot of times when we're trying to root all of these organisms back like this and try to determine the patterns of divergence, it's very complicated, and I would suggest it's complicated because you're trying to trace an evolutionary history that never happened, right? So if these organisms don't actually all share an ancestor, but were instead maybe separate creations, then it should be complicated to try to trace their evolutionary history. Trinity and then Katie.
Well, I don't think.
You don't have a question anymore? Katie.
So what's this group? Like what the so the other group you said had some descendants left out, but what does
Yeah, so polyphyletic is separate ancestries. Or you can talk about it as multiple ancestries. Either way. So notice that this group is only polyphyletic because we're not including some of these ancestors in this group. So if we say changed this, you see where the red is? Let's say the red went all the way, it included this ancestor and it included this ancestor, okay? So we changed the location of that red circle. What kind of a grouping would it be then? So we changed it to include this ancestor, but it's still left off group 4.
Mono.
It wouldn't be monophyletic because it's not including all of the descendants, right? It'd be paraphyletic. Okay, if the shape of this circle changed to include this ancestor, and this ancestor, it's now a paraphyletic grouping. What makes it polyphyletic is that we're not including these ancestors in that group, meaning the members of this group are coming from separate ancestries that are not included in this group. Isa.
So if you were to just circle like 1, 2, and 3, but not the ancestor of 3. Well, actually,
Right, but that's...
Wait, does that even count? Because they don't share a common ancestor there.
Which one? 1, 2, and 3?
The poly-
Yeah, that's the problem with this grouping.
Oh, okay.
Yeah, they do not share a... So, yeah, I mean, they do not share the most recent common ancestor, and so that's the problem with this type of grouping.
So that doesn't work then?
It's just something to be avoided if you're trying to classify organisms based on their evolutionary history, which is what you try to do with systematics. I mean, this is what Chapter 26 is all about. If they're related, then how, right? That's what 26 is all about, and so then how is answered using these phylogenetic trees, and then we try to name them in ways to illustrate the how. Mark.
What makes it monophyletic?
Mono?
Yeah.
There's a single ancestor that unites every single descendant of that ancestor. So what makes a monophyletic is that you are representing a single ancestor and all of the descendants of that ancestor.
So let's say you circle like basically the entire thing.
If we circle the entire tree, it's still monophyletic. Yep, it would just be what you would call a. It would still be monophyletic. You would call it a more inclusive monophyletic group because it's including more species. So Mark asked, what if we just circled the entire tree? If we circled the entire tree, we would still be representing a single ancestor and all of the descendants of that ancestor. It would be a monophyletic group, but it would be a more inclusive monophyletic group than this one. Yeah?
So for
Paraphyletic?
yeah, is it like they don't have the same ancestry?
No, they do have the same ancestry, but we're leaving off some of the descendants of that ancestor. So here's the paraphyletic group. Both 1 and 2 share this common ancestor, but we've constructed our group as such that 2 is not part of it. That some of the descendants are not included in that group. It'd be like one of your children that you ostracize, right? For some reason, the child is forced into being the prodigal son, right? Or I mean, whether they did it to themselves or you did it to them, if they are no longer part of that family, that's the idea of the paraphyletic group, because you have one set of descendants that are not included in that group.
Okay, and for the
Polyphyletic, typically you're leaving off the ancestors. And so because of that, it creates a situation in which you have members of your group that came from separate ancestry. You have members of your group that don't share a single ancestor. I mean, these do if you go all the way back to here, but since we didn't include this ancestor or this ancestor, we can't go all the way back to here. Emma?
Can you just use these to categorize?
Yes, to classify what kind of a grouping it is. And then so we have what are called traditional taxa. And so like kingdom, phylum, class, order, family, genus, species. These are traditional taxa, taxonomic ranks. And so now people want to go and change some of those groups, what they actually referred to try to make it more representative of the perceived evolutionary history. So like the group reptiles, right? Y'all have, when you hear the word reptile, what do you think? A lizard, a snake. What'd you say? A dinosaur? Just wonderful. Okay, any other ideas?
Scales.
Scales, just something with scales. All right, a chameleon, love it. A crocodile, right? Nobody said crocodile. Nobody said turtle, which is sad. Why are we leaving the turtles out? Anyways.
I didn't know a turtle was a reptile.
Oh yeah, absolutely.
Amphibians.
Amphibian. So this group reptiles, it now became kind of an issue. So traditionally, reptiles, that's exactly what people would think, right? They think lizards, snakes, crocodiles, turtles, maybe, but that's what they would think. The problem is the proposed origins of both mammals and birds are that they evolved from an organism that would have been classified as a reptile. And so now reptiles becomes paraphyletic, unless what happens? So if mammals and birds that we put as separate groups came from reptiles, that group is now paraphyletic. Unless you do what? Put all those descendants back into that group. Okay, put birds into that group. And even put mammals into that group. And now reptiles is now monophyletic. Okay? So now it kind of takes on a new meaning. So now if you're talking to somebody that is a big proponent of systematics, using names that are only representative of the evolutionary history, then now reptiles has to mean something different. It has to mean reptiles and also birds and possibly mammals, depending on where you start that group reptile. Alright? Make sense? Okay, may I erase this? Alright. I have one more piece of information I want to give you, and then I want you to work on something with those around you. Okay? So this one more piece of information. Alright, so we talked about homologies versus analogies, right? Which of those two do we use when we're building these trees? Homologies or analogies? Carrie. Homologies, why?
Because it had similar features from shared.
Yeah, they're similar features because of shared ancestry. That's what these phylogenetic trees, these phylogenies are trying to represent, are these shared ancestries, right? So we're going to use homologies. Okay? And I told you before that these homologies, they can be morphological homologies, or they can be genetic or molecular homologies. Okay? But they also come in two different forms. We have shared ancestral features. What does that mean? Shared ancestral features. Yeah.
Features that were in the ancestor, and so they're in the descendants.
Yeah, and they're shared by all of the descendants of that ancestor. And then there's a fancy word for this, and you're gonna love it. A plesiomorphy.
We've heard that one.
Yeah.
Plesiosaur.
No.
And then you have homologies that aren't, that maybe are only in all of the members of a single branch. And so what these are called are shared derived features. Shared derived features. These are the features that we use to actually create new branches. So these aren't features that we're necessarily using to link multiple species together. These are the features that we're using to know when do we need to have a branching event, right? Where we're representing some speciation event. Trinity.
So either one of these, do they have to be shared with all of the descendants, or just like?
So they could be missing. So let's say snakes, right? Some of you said snakes. That's what you think of when you think of reptiles. Snakes are a tetrapod, but they don't have limbs. Because snakes are believed to have lost those limbs secondarily. So they came from an ancestor with 4 legs, but they don't actually have 4 legs. What's interesting is it's not very hard to trigger a snake to develop limbs. They still have the genetic material necessary to produce limbs.
Little long ones with legs, you know?
In the embryo, you give them something that's going to trigger master control genes to develop limbs. Well, pythons, are you talking about in The Good Dinosaur? So in The Good Dinosaur, there's a viper in that movie with legs. It's a Pixar movie. But anyways, pythons and some boa constrictors actually make small pelvic girdles and sometimes some small hind limbs that don't actually erupt. Yeah.
So
Emma.
they're just like they're like
Though they're there like little skeletal elements, but they don't actually even form limbs. They're just the bones. Yeah, Emma.
How long can a snake go without water?
I don't know.
You can walk on it.
I don't know. And I would imagine it would vary a great deal from species to species. Synapomorphy. So these shared derived features that we use to know when we need to have a branching event, these are called synapomorphies. You know a kangaroo rat?
What?
Kangaroo rat?
Is it a rat that jumps?
Yeah, it hops.
Oh my god.
It's the genus is Dipodomes or Dipodomes, however you want to say it. But anyways, they live here.
But he doesn't know how long a snake is.
Well, it's going to vary from species to species. Relax. They go their entire life without drinking water.
What?
No, kangaroo rats.
How do they live?
I'll show you in just a second. Okay, so does everybody have this? Plesiomorphy, synapomorphy. Okay, does anybody remember the equation for cellular respiration? The chemical equation.
Oh.
That's the wrong equation, but that's pretty good. I believe that's the Pythagorean theorem.
Yeah. Wait, what's the equation?
And then what about the quadratic equation?
X equals.
May I erase this?
Plus or minus square root of b squared minus 4ac all over 2a.
Alright.
Do that too.
So, the chemical equation for cellular respiration, or the most common type of cellular respiration. C6H12O6 reacting in the presence of oxygen to form.
H2O plus CO2.
Okay? So water is a product of cellular respiration. So kangaroo rats never drink water. All of the water they get is from cellular respiration. Or from breaking down, not even just even getting to cellular respiration, but breaking down the fats in the seeds that they eat. And in order to break like the fatty acid tails off of a fat, you produce water. Yeah.
Isn't there like
Is that how it works? No. You actually produce water synthesis. I don't know. I'd have to go and look at it. Emma.
What's their average lifespan?
Of a kangaroo rat in the wild? Not long. Maybe just over a year. But I mean, in captivity, and they actually do pretty well in captivity. I mean, they'll live 3 to 5 years. So, and you don't ever have to give them like a little water bottle to drink from, like you would a hamster.
They
You
just live.
just give them seed. All right. Yeah.
Why wouldn't they drive that over the wild?
Because they get eaten.
They just gonna eat it.
All right.
Determine if you have fourth hair or soft hair.
No, it has to do with the particular, not type of keratin that you're making, because it's all alpha keratin, but in what amino acids go into your keratin and how much of a twist you get in it. So people with really like coarse hair, they have a lot of a particular type of amino acid in their keratin, and for some reason I can't think of what it is right now. Maybe it's serine? But anyways, it's an amino acid that nearby amino acids end up linking up, and it creates kinks in the keratin, and those kinks provide for a less smooth structure and provide that coarse and usually also curly or wavy hair as well. Isa.
So what's the skin of
Oh,
the rhino?
you had 2 questions. The skin of the rhino is same as our skin, it's just got more keratin and it's thicker. It would be more equivalent to like the pads on your dog. If you feel that thick pad, that would be like what the rhinoceros skin is going to be like. Emma, your second question. Oh, that's right. I'm sorry. Trinity, did you still have a question? Okay, so now we need a synapomorphy. This is a derived character to separate horses from this ancestor. To know, like, now we have something new. So what do all these horses have? Yeah. All right. How do we spell that? M-A-N-E?
Oh, that's good.
Okay. I'll take that. Yeah. I'll take that. You could also do like the jaw structure, right? That horse has a really long face. Okay, that's from its jaw structure.
What is this?
Oh, the long hair that you have on the back that goes all the way down the neck.
Skin, it's not like leathery.
But we only need one. You want to change this?
No, I was just
Oh,
wondering
sure.
if that was something.
Absolutely. Yeah. And then, okay, now we need to figure out a way to split these 2 groups. We need a synapomorphy. Either one for here or one for here. Either way, we can split these groups.
Right.
Okay, so we'll put that over here. And there are multiple species of zebra, and so that could work. All right. You see these? We've got some features. Yeah, Trinity.
Those little dashes.
They're representing our homologies that connect all of the descendants of whatever this ancestor. Oh yeah, every time you branch, you should be able to put something in there to support that branch, some novel structure. Oh sure, yeah, you can put as many as you want. Oh yeah, sure. Yeah, you can put as many synapomorphies as you want. Okay, now we need to deal with this whole synapomorphy versus plesiomorphy. Somebody remind me the definition of a plesiomorphy. Trinity. Shared ancestral feature. What about a synapomorphy? Lydia. Shared derived feature. So this right here is a synapomorphy for this group. Do you agree? This is synapomorphy for this group. This would be a plesiomorphy for this group. Because it's something that you still find in all of these groups, but you have to go before the most recent common ancestor of those groups to get to where it appeared for the first time. Okay? So this is a synapomorphy for these groups that appeared for the first time in this branch.
Oh, I see.
This is a feature still present in this branch, but it appeared for the first time before that branch even existed. Right? So synapomorphy, plesiomorphy. Synapomorphy, plesiomorphy. Let's look over here. What about main? Main for this branch here, is it synapomorphy or plesiomorphy? Synapomorphy for this branch, but what about main for this branch? It's a plesiomorphy because it's a feature that was present before this ancestor. It existed before this ancestor even existed.
Let's talk about mains there. But if we're doing
Yeah.
stripes, it'd be different?
If it were doing stripes for this branch, it's nothing because it's not even a feature of this. But for zebras, stripes would be a synapomorphy.
Why is mains a synapomorphy, not a
Well, it's a synapomorphy if you're talking about this entire branch because it appeared for the first time in that branch. But if you're talking about these later branches, it appeared before those branches existed. So it can't be a synapomorphy, something that appeared with that branch, because it existed before the branches existed.
But stripes is synapomorphy, so
Yes.
that would be whatever was over there. What was over there?
This, I don't know, we didn't write anything. But this would be a synapomorphy for this branch.
Oh, I thought you said it was a plesiomorphy.
No. Mains is a plesiomorphy for this branch.
Why is it a plesiomorphy for zebra?
Why is mains a plesiomorphy for zebra?
Why isn't it?
Oh, it is.
Oh, you just
No, stripes is a synapomorphy. Main is a plesiomorphy for zebras.
So one feature is the first time which appeared in creature, and is a
Yeah, so the best way to just think of it is if it is a feature that appears when the branch first originates, then it's a synapomorphy. If it's a feature you use to know that you have a new branch, it's a synapomorphy. But if it's something that existed before that branch existed, it's a plesiomorphy. Now, look at this. Here's where it gets fun. This, we talked about, it was a plesiomorphy for this branch, right? Odd-toed ungulate ankles is a plesiomorphy for this branch. What is it for this branch?
It's nothing.
It's still a plesiomorphy. It's a feature that you'd expect to find in all of these groups, but it existed before this branch even existed, right? It's all the way back here. But what about for this entire group? It's a synapomorphy now because it's what allowed us to define this branch. So if you're considering all of these organisms, horses and rhinos, this is a synapomorphy. But if you're only considering rhinos or horses, it's a plesiomorphy. Again, you have to think about it this way. If it's a feature we use to define that branch, it's a synapomorphy. If it's a feature we used to define that branch, it's a synapomorphy. Right? It's what allowed us to know that branch exists. If it's a feature that you find on that branch, but it existed before that branch existed, then it's what? It's a plesiomorphy. We'll do some more practice with this. You'll love it. I'll love it. We have one more thing from chapter 26, and then we'll be in a great place to take ourselves a break.
I like bricks.
I like breaks too. Okay.
Who doesn't like breaks?
Some people like them.
Corporations. All right. Or a sports team that's really got a lot of momentum going. They don't like breaks.
Is that
You
a new
know?
shirt?
Like
No.
the Rams.
Like the Rams. Yeah. But the Rams they don't have a bye week this week.
I don't know.
They don't. They play New Orleans. Oh my goodness. They play New Orleans, which may be a preview of the NFC Championship game.
Probably.
All right. Okay, may I erase this?
Yeah.
All right.
Who has a bye this week? Someone has a bye this week.
All right.
I have a bite this week.
The Eagles do. The Giants do.
And
Everyone on my flex. Any person that I just had to start a flex.
The Eagles just picked up Golden Tate.
The big trade's gonna be Dante Fowler Jr. to the Rams.
Yeah, either that.
That's stupid good.
Yeah, either that or Demarius Thomas to the Texans.
That's a big one too.
That's a big one because that division is very easy to win. All right. Okay. So let me present to you a problem. Okay. So here's our problem. What if we can produce?
Sorry, I was reading in the board.
What if we can produce multiple? Oh gosh,
That was
that's.
the ugliest piece I've ever seen.
What if we can produce multiple phylogenetic trees?
Why not? Wait, so
So,
you're
like
saying,
with what we were doing in our previous exercise, what if instead of putting horses and donkeys together, we put donkeys and zebras together to the exclusion of horses, right? So what if we can produce multiple phylogenetic trees? How do we know? How do we know which tree is correct? Okay, how do we know which tree is correct? And I'll tell you, we don't know for sure, but we have some ways in which we can try to figure out which tree is most probable. Okay? So how do we know which tree is correct? Now what's fun with this is, if you believe that many different groups of animals were created separately by God, then what you're doing, if you're trying to connect those independent creations, no tree is correct. But assuming, again, chapter 26 is, if they're all related, then how?
How did we know? How do you?
My O's have had tails. Sorry. What's that?
What do you mean
By
by correct?
correct, I mean it's actually representing what happened in evolutionary history.
How do you know?
So is our phylogeny
Yes.
tree is correct?
Yes. Yeah. It means it's actually representing what happened in the past. Yeah. Okay. So we have two strategies. Just two. Just two. Not three. Not four, but not all, more than one. We've got two strategies. And they are called maximum parsimony. Maximum parsimony. And we're all having issues. And it's a Thursday. Usually this is like a Monday vibe. Like where people are like a little tired, but like very distracted. We're all like the dog from Up. Squirrel. Right?
That's me
Which-
every day.
Okay. The other one,
This is like Monday. Well, it was right after Halloween, so
I know.
although I didn't stay up 2 weeks. Never mind.
The other one is maximum likelihood. Okay, so we have two strategies: maximum parsimony maximum likelihood. Oh, I'm going to tell you right now, don't you worry. Maximum parsimony, maximum likelihood. Okay? Maximum parsimony, maximum likelihood. Yeah. Okay. So these are, remember, we're almost to break time. I'm going to have to cancel break time. Oh,
That
yeah.
would just make things worse
Oh.
for you.
No, it would make things worse for you. It would keep things the same for me. It's really. Alright. So maximum parsimony, maximum likelihood. Maximum parsimony, this is the strategy. Okay. Whichever tree requires the fewest speciation events is best. Whichever tree requires the fewest speciation events is best. Okay? So that's maximum parsimony. Whichever tree requires the fewest speciation events. Sometimes you'll see this referred to whichever strategy requires the fewest evolutionary events. Okay, but we're talking about speciation events, right? Taking a species and splitting it into two.
So basically, the simpler the better.
Yes, the simpler the better.
Likelihood is a really weird word.
I don't think it has an E.
I don't think it has a.
I think it does.
I don't know.
What? I'm not. Anyways, I don't. Oh, it has an E. Oh, wait, I mean, at least according to the textbook. All right. So maximum likelihood. Whichever tree requires the most likely genetic changes is best. So you have to keep in mind that if you're going to have some kind of a speciation event, you need there to be variation, right? You can't get reproductive isolation just because forms are separate unless there's also variation that can start to make them different, right? Like our cheddar versus pretzel fishes. So whichever tree requires the most likely genetic changes to get that variation, that's the tree that's best. Okay? Are these differences, do they make sense? So this one doesn't care about the number of speciation events. Because it's like there are some genetic changes that are very common, other genetic changes that are not as common. So it doesn't really care how many speciation events there are. It's just whatever's easiest to accomplish genetically. That's what's going to be the best tree. This one, it doesn't care about which genetic changes are more or less common. It's just trying to use the fewest number of speciation events. Michelle, did you have a question?
Yeah, I'm still kind of confused. The difference between those two strategies.
So again, so for maximum parsimony, you're just trying to get the fewest number of branches. Whichever tree has the fewest number of branching events. For this one, you don't worry about how many branching events there are. You're trying to emphasize what are the most likely means by which you can accomplish those branches. So this tree may produce you a tree with 20 branches, but all 20 of those changes are very common genetic changes. This tree may produce you something with 15 branches, fewer branches, right? But some of those branches are very difficult to accomplish genetically. It would require very complicated genetic change to make that branch happen.
Wait, so both two are like flat?
They're just different strategies. They're different ways of trying to figure out what the best tree is. So they're two completely different strategies to try to determine the best tree.
But the maximum likelihood is like
easier to accomplish genetically. This one's easier to accomplish through speciation events, right? The fact that you actually have to separate organisms reproductively in order to have a speciation, right? All right. We okay?
Yeah.
Okay, it's 9:03. We have finished chapter
Is there a dog there?
No, Musk. All right. Yeah. Shh. So we're back. You gotta wait. Sorry. Okay. Whoa. Yes.
Is there just things like is there a dog?
Oh, I don't even know. All right.
There a dog.
So we finished chapter 26, and now we are very quickly going to move through chapters 2 and 3. And the reason why we're going to do this quickly is it should be review of almost the very beginning of honors camp.
I feel like that was our entire year summed up in one chapter, and it was a little sad.
No. No way.
Yeah, like,
Okay. So
oh yeah.
a big part of understanding why living organisms work the way that they do is understanding bonding and and the implications thereof. Okay? And so in order to understand bonding, you have to remember that we essentially have two broad categories of bonds. Okay? We have ionic bonds and we have covalent bonds. Ionic bonds involve the transfer of electrons. The transfer of electrons. Okay, so ionic bonds involve the transfer of electrons so that you end up with something like this. So here is our nucleus. Okay. So draw these two atoms, please. Draw these two atoms. Okay. So you'll recall that this innermost energy level typically holds a maximum of 2 electrons, right? It's an S, and it's the 1s. And so in that first energy level 1, you only have S subshells. But then once you get to 2, you get S and P, and then when you get to 3, you get S, P, and D, and when you get to 4, is it 4 or is it 5 that we get F for the first time? It's 5F and 6F, I think. Anyways, yeah. So then you can get S, P, D, and F. Okay, anyways, alright. So we're looking at this. So this innermost energy level can hold 2 electrons, and then everyone outside of that typically likes to hold 8. Okay, this is how we do it. It's not actually the way that it works exactly. Well, as far as we know. But it's a nice way to simplify this. Okay. Those are E's, by the way. E is for electron. Love it.
So that would be.
Oh, it's not confusing.
No, I get it, but like,
No, that drawing is beautiful, is what you meant to say. You say, Dr. Engel, not only is that drawing beautiful, but it is so informative. And you're like, I never understood a picture is worth 1,000 words until this very moment when I looked upon your drawing.
Exactly how good.
Yeah. Okay, so How many electrons are in this third shell of this atom here? 7. So this atom, it's hungry. It's hungry for electrons. Okay? It's hungry for an electron to fill this outer shell. This atom right here only has this inner shell, and how many electrons does it have? It has 1. Okay? And so this thing it's not very hard to lose that 1 electron, because if it's only got 1 electron, it only has 1 proton in the nucleus holding on to that. Okay? And so it's not very hard to lose that. Yeah, Isa.
The outside layer has 7, right?
Yes.
Is that because the other one has yeah, so it's trying to take that.
So this one needs 1. This one has 1 to give. Okay? This happens to be hydrogen, and this happens to be chlorine. Right here.
Yes, yeah.
So now I'm all okay. Sorry. So chlorine, it should have 17 electrons. We've got 8. We've got 7, which is 15, and then 2 more is 17. Okay. So this is H. This is Cl. Okay. This has an electron to give, and this desperately wants an electron. Okay. And so you're going to get a transfer of this electron into that position. So let me do this in red now. This is gone, and that has transferred over to here. And so it is hydrochloric acid. So if hydrogen used to be neutral, and now it lost 1 negative charge, what charge does this hydrogen now have carry? It has a positive charge. And this is now a hydrogen ion. Okay? A hydrogen ion. Right? Different, there are more or less electrons than there are protons. So it bears a charge. This chlorine used to be neutral, but now it has taken on an extra negative charge, and it has a negative charge. And in ionic bonds, positively charged ions are attracted to negatively charged ions, so you form HCl. Hydrochloric acid. All right? We love it, right? Chemistry.
For one day. They exploded the paper when I left.
No, but you would have stayed if it weren't for me. Yeah, I know. Trinity's, complimenting my drawings today. You're just complimenting just my person. I mean, I feel so great. I feel so great. So covalent bonds. You did tell me that. Covalent bonds involve the sharing of electrons. The sharing of electrons. These do not involve the transfer of electrons. They involve the sharing of electrons. Sharing is caring. Okay? And covalent molecules know that better than anyone. Oh, we're going to draw one. You better believe it.
Of course. This is art class.
Oh, you just wait.
What are we drawing?
Oh, why am I doing solid now? Man,
Inconsistent.
I'm sorry. I want this to again be a very clear.
Okay, but why are you doing
Why am I doing what?
the dot? Does that mean it could be moved?
Yeah, the electrons are free to move. Do you remember the Heisenberg uncertainty principle?
Yes.
There you go, where you cannot simultaneously know the location and the direction of an electron. Okay, it's all coming back. It's coming back to me now.
Don't let us do that. Don't plan on it.
Oh my gosh.
They both want meat and they're valence shells, so
How many do we have? We only got 6 that time.
We only have 6
Okay, so it's 8.
in the outer shell.
Now we got oxygen.
Yeah, both of these are oxygen. Nicely done.
8 and 12 of them?
Literally count them.
May I-
and look on the periodic table.
Hey, may I call you Richard?
I mean, first of all, it's not my name.
Oh, I know it's not your name. May I call you Mr. Roberts?
Sure.
Okay. Thanks.
Why?
I don't know.
They just want or bishop.
All right. So both of these are oxygen, and both of these have 6 electrons in their outer shell. That's not good. They want 2. And so they can either find 2 atoms of hydrogen wanting to give their electrons, although they'll share them as well. Or they can do this. And now they are sharing 2 sets of electrons. They're sharing 2 sets. Right?
double bond.
So we got a double bond.
Whoa.
Why are we learning this?
Because it allows us to understand why things work the way they do at the molecular level. This section of our class is molecular biology. And so in order to understand how things work at the molecular level, you've got to understand bonding. You've got to understand bonding. Yeah, Trinity.
So they're like.
What's that?
Wait.
So they're sharing 2 sets of electrons. And so what this would actually look like is you actually create a new orbital. You actually create 2 new orbitals. And that are, did you all do molecular orbital theory?
With the, like different weird shapes.
Yes.
Oh,
You probably did like hybridization, where you would take, so in this case, these would both be p electrons. These are p electrons, because this,
What does that mean?
That's the shell.
yeah,
The S shell and the
there, it's, so we've got these, the first 2 electrons are in 1s, and then in 2s, and then 2p. So these are all 2p electrons, and when you hybridize 2p orbitals, you form one orbital that's in plane, and then you form an anti-bonding orbital and a second bonding orbital that's out of. It gets very interesting. But anyways, molecular bonding is based on quantum mechanics and seems to be a more accurate picture of what's actually happening. But anyways, it's super complicated. Suffice it to say that they are sharing 2 sets of electrons, and the sets are in a new orbital that didn't exist before the bonding. But either way, anyways, they are sharing electrons. These electrons did not transfer from this oxygen to this one, nor did these electrons transfer from this one to this one. They are sharing them. Yeah, Michelle.
Why do they share?
Why do they share? They share because the affinity of both atoms for the electrons are the same, or close enough that they can't strip them away, is essentially what it goes to. So this oxygen wants electrons in the same amount that this oxygen wants electrons, so this oxygen cannot strip the electrons away from this.
But they're not like sharing it.
They are sharing them. So because they can't strip them away, they're actually sharing them.
Oh.
It's like, you have something I want. If I cannot take it from you, we'll share it, right? This is the way like siblings work, right? You have something I want. I may not be able to take it from you, so we'll share it.
Yeah.
But we'll get to that.
What's mine?
Katie.
What's the name of this chapter? My brother's pajama.
This chapter? I don't know. I'm sorry. I should know the answer to that question, but I don't. Does anyone know the name of chapter 2?
Oh, it's chemical or
Molecular.
It
No, it's
has,
like
it
chemical structure.
has all games down the
Sorry.
front.
Okay, so we've got ionic versus covalent. We okay here?
Yes.
Alright. And then so in chapter 2 it also shows you how to represent this with chemical equations and reminds you that chemical reactions, which if we're going to form oxygen, a molecular oxygen, we have to have a chemical reaction to form this from oxygen atoms. Although, anyways, happens spontaneously because the oxygen want that filled outer orbital. But chemical reactions involve moving atoms from one molecule to another, right? Chemical reactions do not create atoms. And unless it's a nuclear reaction, do not destroy atoms. Although nuclear reactions, some atoms are destroyed, but they're still atoms. They just lose some of their pieces, right? It's like the Dodgers after they allow Manny Machado to leave and wish they could get back all the prospects that they gave up for him for his 273 batting average and then for his 2 for 22 in the World Series. All right, but he does run over people's ankles. All right, Katie.
Give me secret.
Wow, I pulled off a scab and it's oozing. All right.
Sorry.
Okay. All right. So we okay with this? So chapter 2 again, it also talks about chemical reactions, and in chemical reactions, what we're doing is seeing this type of thing happening. Transfers of electrons. This would be like an oxidation reduction, would involve something like this, or acid bases. All right. May I erase this? Because we have a particular type of covalent bond that we need to talk about that chapter 3 is all about. Okay. So this was a 15-minute summary of chapter 2, which chapter 2 was a 23-page summary.
This is it. That was it. I bet that.
Oh, that was it from chapter 2.
What we just did, that was it.
That was it. Okay. So,
Whoa, no way. That's crazy. Emma didn't ask any questions.
Okay.
all right.
Not that many.
Wow, you guys are so rude to each other.
I know. I'm trying to
We're a family.
Polar covalent. Okay. Shh. Yeah, it hints at it a little bit in chapter 2, but we are moving it. Yes.
Wait, but we didn't learn this.
Wait, somebody else ask. Somebody else. We need one more. Yes, it is. Okay, good.
Wait.
Alright. No, with 3 is enough. 3 is enough, Rick.
Really?
Let's not join the party.
Hitting me, Rick.
Alright.
100%.
So I know it's hard to even know what's happening in here because it's crazy. Okay, so polar covalent bond involve an unequal sharing of electrons. Okay, so for 15 years, my brother and I shared a bedroom. From the time of his birth until he was 15 years old and I was 17. My brother and I shared a bedroom. No, that I was 17, I got my own room. My sister moved out, and I got my own room for 1 year, and then I moved out and never came back. Anyways, so a polar covalent bond, they're still sharing the electrons. One atom hasn't completely stripped it away from the other, but it is not an equal sharing of electrons. So for 15 years, my brother and I shared a room. Okay? But it was not an equal sharing of that room. My brother had his bed and nothing else. Right? My brother had a place to sleep. I had a bedroom. Right? And so this, in a polar covalent bond, let's do something like this. I'm going to make it a little bit simpler. I'm not going to draw all the orbitals.
Can we please?
No, we cannot. Sorry. So remember, oxygen, how many electrons does it want? We already drew this. It wants 2. So desperately. So desperately. Hydrogen, each hydrogen has how many electrons to give? 1. So if it's going to form a relationship with hydrogen, it's going to need 2 of them. Now, Oxygen wants those electrons. Hydrogen has an electron to give, but oxygen does not want them strong enough to actually strip them fully away from hydrogen. So they share them. But it is a very unequal sharing. So right now I've drawn this, see here's a pair of electrons that they are sharing, and now hydrogen has 2 electrons in its inner shell, right? The only shell it has, right? So it's got 2, and that's how many electrons you want in that inner shell. This one has 2, and now this oxygen has 8 in that outer shell, how many it wants. Okay, so I drew this with the illustrating the shared electrons. But in reality, it looks more like this.
That's the delta positive, delta negative.
Those electrons are spending way more time with the oxygen than they are with the hydrogen. They are shared, just like, oh gosh, you guys don't even know about the original PlayStation. Have any of you played on an original PlayStation? Yeah, Nick. So, it's PS4 now, right?
Yeah.
They haven't come out with the 5 yet. So, well, first of all, my brother and I had an original PlayStation. My brother and I had an original PlayStation. We technically shared it, but it spent way more time with me than it did with my brother. And then when the PlayStation 2 came out, my brother and I went and sat in a 24-hour Walmart back by the layaway for 23 hours in line to be able to have an opportunity to buy one of the 20 PlayStation 2s that they had. Well, we did. We did. My brother and I waited together for 23 hours. We were supposed to get 2, but then we got up there and they said, no, you could only buy 1 per family. So we bought it.
What if you said you just weren't brothers?
I know, right?
So
That's a really easy fix.
unless you see my brother and I.
Oh.
It's not quite like Kyle and Brandon, but it's close.
So cute.
My brother and I look very at this point we looked very similar, and then my brother lost a bunch of weight and now we don't look all that similar. But at this point in our lives we did. Anyways, and then we got home and my dad's like, dude, these things are going on eBay for like 4 times what you paid for it. Sorry guys, I'm selling it. And they sold our
No.
PlayStation 2. Yeah, and then we had to wait like 4 months. Yeah, and then we had to wait 4 months for them to actually be able to meet the demand, and then we find. Anyways, sorry. This is like giving you a snapshot into my junior high life. All right, so they are sharing these 2 electrons, but those electrons are spending far more time with the oxygen than they are with the hydrogen. Okay, and so remember, this oxygen was neutral when it was still missing 2 electrons, right? It wanted 2 more electrons in its outer shell, and it was neutral at that point. Now, if it has those 2 more electrons that are spending way more time with the oxygen than they are with the hydrogen, we have a slightly negative, it's actually not slightly, it's pretty negative pull in this water molecule. So around the oxygen, we have a pretty negative charge.
What's that little sign?
Delta.
Delta. It's a Greek letter. Let me draw it better. So we've got a negative pull, and then the hydrogen, they were neutral, and now their electrons are spending a lot more time away from their atom than they are with it, and so now these hydrogens
It's like an 8 if you don't finish it.
have a net positive. And so we create what's called a polar covalent bond, where we have a negative pole and we have a positive pole. Okay? And water is polar. Water is about as polar as you can get before it just would be an ionic bond.
It isn't why. It's like a
That's
whole
why it breaks
equilibrium
things
thing.
up so well.
Yeah.
Oh yeah. Oh yeah. And this is what chapter 3 is all about. Chapter 3 is like, hey, water is polar. Because water is polar, it can do very, very wonderful things. And so there are 4 big characteristics of water that are true because water is polar. Okay? There are 4 big things about water that are true because of how polar water is. Not that it's polar, but because of how polar water is. Again, it's about as polar as you can get and not be an ionic compound. Okay? First thing that's true about water is what's called cohesion. Cohesion. Have you heard the term adhesive? What is an adhesive? It allows something to stick to something, like a Band-Aid sticking to your arm, right? Or your face if you've got a cut on your face. That always looks pretty legit when you've got a Band-Aid on your face. Or better yet, if you take out like a suture kit and you suture your own face with no anesthetic.
It's like
Stitches.
That's cool.
Yeah, it's pretty. Anyways, cohesion is when two of the same material stick together. Emma.
What are dissolvable sutures made
Oh, I don't know. But I imagine that they're probably something that just gets broken down by the constant exposure to moisture. So it's probably made out of something that dissolves in water and just dissolves slowly. Yeah.
Could you define
Cohesion, and so this is they stick together. Water molecules stick together.
Molecules stick together?
What's that?
So two of the same molecules stick
Yes. So that's cohesion. And this does wonderful things for water. It's so as a plant loses water through transpiration, water is pulled up to take its place because of these water molecules sticking together. Lydia and then Mark.
Okay, this is just a question about sutures. Are like the sutures like after like meniscus repair, are those dissolvable?
Yes. Typically. Mark.
They kind of like on the top of the on the thing that Emma mentioned, where like what those things are called, what are they called?
Sutures?
Sutures. So like those two, you said those things dissolve in the great, like it was just a bunch of moisture.
Yes.
So let's say you just put that in the middle of just a rainforest where it's all humid and stuff like that. Would you just dissolve it in its own?
Yes. It's the same thing with biodegradable toilet paper. So like when you go camping, you're supposed to take biodegradable toilet paper. It breaks down much more quickly than regular toilet paper. And a lot of it has to do with its interaction with water. Okay, so water has a very high specific heat. And what that means is you have to put a lot of energy into water to get it to heat up. Or you have to pull a lot of energy out of water to get it to cool down. Yeah, Emma.
It's kind of a weird question. Like, when you drink a lot of water, your urine's like clear.
Yes.
When you don't, it's like yellow.
Yes, that's because it's more concentrated when you drink less water, and it's primarily urea.
it's primarily your what?
Urea is it's a molecule. It's a metabolic waste. It's a nitrogen containing waste that comes from metabolizing proteins. So the more water you drink, the more dilute your urine is because you have to maintain water balance. And so the best way, if you have too much water, to get rid of excess water is in the urine. But you need water to get rid of the urea, which is dangerous to build up. So you don't want that building up. So you have to use water to get rid of it. That's one of the reasons why you have to drink water. Plus you lose water to keep your body cool. Evaporative cooling. You ever notice you weigh less in the morning than you do when you go to sleep, even if you weigh yourself before you urinate?
Yeah.
It's because all night, to keep your body cool, you are evaporatively cooling. Mostly through your mouth and your nose. Like you're losing a lot of moisture to keep your body cool.
When you're losing water.
Okay, liquid water is more dense than ice. Oh no, we're out of time. We'll have to get the fourth. We'll have to get the fourth on Monday. Okay? So here are three very special things about water that are all